Hi there, welcome to week 3 of the HackadayU serial buses course. This week we're going into OneWire, which is a really cool serial bus used in low power devices and low power sensors and such. Again, I'm Alexander Rowsell. There's my email address on screen. And let's jump into it. So a quick intro to what OneWire is. It's an asynchronous serial protocol that was originally developed by Dallas. I couldn't find any references exactly to when it was developed, but it was patented in 1989. It's similar to I2C in that it uses an open drain device connected together in a common bus with a pull-up resistor. So all the devices connected to the bus can only pull the bus low, and they require an external pull-up resistor to keep the bus high. This has the same advantages as it does on I2C. In that the default state of the bus, for example, is a safe state where things, you assume that things aren't connected. The power line is optional. This is a really neat thing about OneWire and why it's called OneWire. Literally all you need to communicate with it is one wire, which does data and power, and of course a ground. Technically it's two wires, but ground, we usually don't count. So it uses this thing called parasitic power mode, where it literally will store charge from the data bus. It'll actually use the high state of the data bus to store charge, and then when it gets communicated with, it uses that stored charge in order to respond or whatever it needs to do. Every device has a unique 64-bit serial number. This is one of the distinguishing features of OneWire as opposed to I2C. Where in I2C you could have multiple devices that were identical, but they all shared the same I2C address. On OneWire, every single produced device has a unique 64-bit serial number. So you can have as many of the same device as you want on a bus, and as long as you have all the serial numbers in your code, you can communicate to as many as you want. There's lots of different devices available. There's, often EEPROMs up to 64K, temperature sensors, real-time clocks, battery monitoring, which can be really useful in low-power devices, and acting just as a silicon serial number. Literally just having that 64-bit serial number can be used to identify an individual board that gets installed into, a device somewhere in case you need to know exactly which board it is. Make sure it's been swapped out with the correct board, validate that it is a valid device that was manufactured by you, that sort of thing. So let's jump into the hardware level stuff. It's similar to I2C, so they all connected with an open drain transistor, and a fairly strong pull-up resistor keeps the bus high when it is idle. Unlike I2C, where you'd see 10K to 47K, with OneWire you're likely to see sort of 4.7 to 22K, slightly stronger pull-up. Devices can optionally connect to a powered bus, so they can also connect to VCC and act in sort of a 3-wire mode where they have power, data, and ground. Or they can just act parasitically and store power from the actual data bus in an internal capacitor. The bus runs at a much slower rate than I2C, by default about 16.7 kilobits per second. There is an overdrive mode where the speed is multiplied by 10, so you get 167 kilobits per second, which is slightly faster than I2C's default 100 kilohertz mode. But, not super fast data rate, but reliable and low power. The only limiting factor to the number of devices on a bus is capacitance. Just like with I2C, the more devices you have on the bus, the more capacitance you have. That can start to cause problems. Technically, there is 1.4 times 10 to the 19 unique serial numbers, so they're not going to run out of serial numbers anytime soon. So the parasitic power mode, which is a defining feature of OneWire. Because the power line is optional, devices need some way to store power for when the bus is pulled low. Because just like in I2C, the bus being pulled low is how you communicate. So a diode connects the data line to an internal capacitor, typically about 80 picofarads. And this value is kept small intentionally to avoid loading the bus with too much capacitance. Of course, you could whack a great big capacitor in there. That's going to affect your communication on the data line. So they use as little capacitance as they need to store some charge in order to respond to this bit. And then, the next time the bus goes high, we store a little more charge, we respond to the next bit, that sort of thing. So, yeah, to power the bus logic when the bus is pulled low, or of course, the one-wire device itself has to be able to pull the bus low, so it uses the stored charge in the capacitor to do that. Yeah, the resistors are typically smaller, as I said, typically 0.2K to 2.2K, so it varies, but again, it's usually quite a bit of a stronger pull-up, especially if it's operating in parasitic power mode. That way it charges that capacitor faster, and you can handle more devices on the bus more easily. So as you can see, it's a pretty simple device. We've got OWD, which stands for one-wire data. Ground and VCC. That one-wire data can be pulled to ground by that transistor. You turn that transistor there on, and the drain will be connected to the source, and it'll connect it to ground. It's got that diode so that when the bus goes low, it won't immediately drain that internal capacitor. It can be used to, for example, turn that transistor on or sample the state of the bus. It's got an internal VCC, which is derived from that capacitor or from VCC itself, which powers the internal logic, whatever that may be. And then it's got a ground wire, and that's it. So pretty simple. So why do we have this external strong pull-up being so strong? Well, what happens if the one-wire device needs more current than the bus can provide? Because we have that pull-up resistor, it limits the amount of current that can flow into the device. Some devices might need a peak current 5 to 10 milliamps if it's doing a temperature measurement or some A to D or D to A conversion, something like that. Much more than most data lines are configured to provide. So in this case, the controller can connect VCC directly to the data line for a predetermined amount of time. This is done by using an external transistor typically, or configuring the output pin to be a regular output pin instead of an open drain, and then setting the output high. This is effectively the same thing as enabling an external transistor. It literally just connects VCC directly to the data line. Most microcontroller GPIO pins are capable of sourcing up to 20 milliamps. So if we're going to use an external transistor, this is what that could look like. So here's a sort of typical bus. We've got our microcontroller, and we've got a whole bunch of devices, DS2401 serial number, a temperature probe, 4K EEPROM, battery, fuel gauge. They're all connected to that same one-wire data, and they're all connected to ground, and that's it. So all of these devices in this example are running off of the parasitic power mode. Now, for some of these, like the temperature probe or the battery fuel gauge, in order to do measurements, they might need more than what that pull-up resistor can provide. In that case, the microcontroller can switch on that resistor, or that transistor you see just to the right of VCC there, and that will literally connect VCC to the one-wire data bus and temporarily turn the data bus into a power line so that the devices can draw more current. It's a really elegant way to do it. That way you keep all the complexity near the microcontroller, and then down the line, which could be a fairly long distance. In the case of some of these things like a temperature probe, it might be connected to a wire that's sort of snaking through your device somewhere else. So we can send, strong power down that line and overcome any capacitance on the cable or whatever. And we do it for a predetermined amount of time. So we might tell it, do a temperature measurement. And we know from looking at the data sheet, okay, it needs 50 milliseconds of strong pull-up or whatever it may be. We turn on the strong pull-up for that long, and then at the end we turn it off and we get the results back. So let's look at the protocol level. The hardware level is pretty simple, so let's jump into the protocol. So one-wire signaling. Because one-wire is asynchronous, all communication is done in terms of absolute timing. So instead of being connected to a clock, everything is done based on real amounts of time passing, 5 microseconds, 10 microseconds. It's very specifically defined. Every one-wire bit is sent within a certain amount of time, typically called the frame time or the bit frame time. So each bit has to be sent within a certain period of time. For devices running at the normal speed, this frame time is about 60 microseconds, roughly the period of a 16.7 kilohertz clock. Timing is not super precise because the peripheral devices use a simple RC timer internally to measure time. They're not very precise, they vary quite a bit over temperature, so these timings are important to meet, but they're not so strict that if you're off a few microseconds in either direction, it's not going to work. They have quite a bit of tolerance built in. All communication starts at 16.7 kilohertz and can optionally enter overdrive mode with a special command. And again, when we're in overdrive mode, the bit time is 10 times faster, roughly 6 microseconds instead of 60. So there's something called the sample period. Every time the bus is pulled low by the controller, so no matter what's going to happen next, be it a read or a write, a timer starts inside the device. After roughly 15 microseconds, the device samples the state of the bus. So after that amount of time has passed, it looks at the bus to see what's there. If the bus is high, it's reading a 1. If it's a low, it's a 0. Because the timer is imprecise, that sample time is supposed to happen, it can happen as early as 15 microseconds. It can take as long as 60 microseconds. So we usually, if we're sending a 0, we'll keep it low that entire time. And if we're sending a 1, we'll keep the bus low just long enough to start that internal timer and then let the bus return to high. So that 16.7 kilobits per second speed is an upper limit on the speed of communications. You can go a little bit slower than that, but typically you can't go faster than that or else the devices will respond. They have filters to filter out transient spikes. So if you go too fast, they won't be able to communicate back or acknowledge you. Unless you're in overdrive mode, in which case that's a whole separate thing. They turn off their internal filters usually, and then they can respond more quickly. So there's no issue with going slower than that as long as you stay under the maximum signaling time per bit. So this is where it gets a little bit sort of hand wavy, that each bit does not necessarily have to take up the same amount of time. They sort of have an upper maximum of 120 microseconds, where we start with that pulling the bus low for 5 to 10 microseconds, then it reads the state of the bus. Then we have a little bit of time after that where the bus is guaranteed to be high so that the device can charge up the internal capacitor. These times can vary a little bit, and as you'll see, I typically design around sort of the maximum lengths so that it's sort of guaranteed to work even if it's a bit slower. The only really critical time is the time between the bus going low and the bit being sampled. So if you're trying to send a 1, for example, you have to make sure that you've let go of the bus before 15 microseconds have passed. If you hold it low any longer than that, it's going to read it as a 0, or it could potentially read it as a 0. As I said, each device is going to have slightly different timing because of that RC oscillator. So if you want to send a 0, we might hold it for even longer than 60 microseconds. But if we want to send a 1, we might only hold it low for 5 or 10 microseconds. Yeah, many datasheets will recommend that the total bit time not exceed 120 microseconds. That gives it time to recover afterwards. So let's actually look at a practical example of what this looks like. To send a 1, the controller pulls the bus low for at least 1 microsecond. That's the very, very minimum. Typically they'll say about 5 microseconds, anywhere between 1 and 10 microseconds. It must not keep the bus low longer than 15 microseconds or it'll be interpreted as a 0. So this is what that looks like. Over on the left there, you can see the bus gets pulled low. It's pulled low for about 8 to 10 microseconds. And then it's high for quite a while, about 110 microseconds. So that's that full 120 microsecond bit period that we were talking about. That's a 1 being sent. That's all it is. You pull the bus low and you let go at a certain time. It allows the pull-up resistor to bring the bus back to the high state, and then it waits until that bit frame time is over, at least 55 microseconds later. So that's 55 microseconds plus that 10 microseconds we had the bus low. So again, at least sort of 60 to 65 microseconds per bit, which again works out to the 16.7 kilobits per second clock rate. Clock rate, because there's no actual clock. Sending a 0, we pull the bus low for at least 15 microseconds, typically up to a maximum of 120 microseconds. So here's a 0 being sent. We pull the bus low. We hold it low for, let's see, 10, 20, 30, 40, 50, 60, 70, about 80, 85 microseconds. Well, long enough for it to detect that it's a 0. Then we release it and let the bus stay high until that 120 microsecond bit frame is over. Again, that gives the device time to charge up its internal capacitor a little bit. Yeah, it's going to sample the bus about 15 to 60 microseconds. So, we make sure that we keep it low for that entire time, and then we wait until 120 microseconds for the next bit. So reading a bit, this is sort of the opposite, of course. In order to read a bit, same with I2C, you must have sent a command to the peripheral that requires a response. So the peripheral must be expecting read slots, or else it's going to just think you're sending more data. So you issue something called a read slot. This is signaled by, it's just like signaling any other bit. You pull the bus low for 5 microseconds, and then you let go. The peripheral device will see the bus being pulled low. If it wants to send a 1 to you, it does nothing. It lets the bus be pulled back to the high state. After we let go of the bus, we wait 10 to 15 microseconds, up to 60 microseconds, and then we sample the state of the bus. If it wants to send a 0, it sees us pulling the bus low, and then it holds it low after we let go. And we wait, 5 or 10 microseconds, sample the state of the bus, and then we can see that the bus is still low, so the peripheral must be pulling it low, therefore it wants to send a 0. We'll sample the state of the bus around 15 microseconds after it issues the read slot. When we're reading from the peripheral, we kind of want to tend towards the minimum amount of time, because it's possible that if we wait too long to sample that it might have let go of the bus by then. So we kind of want to keep it on the sort of shorter end of things. And of course, it's just the state of the bus corresponds to the bit being sent by the peripheral. It looks quite similar to writing bits. If you're just looking at the bus and you don't know what's going on, it's almost impossible to tell who's talking. Same with I2C, unless you look at the address and see if it's a read or a write bit, like with I2C, you wouldn't really be able to tell what's going on, which direction the communication is going. But the devices on each end know what's going on. So there's a 1 bit being read. The controller pulls the bus low for that, 5 or 10 microseconds, lets go. Later on, it pulls it low, and as you can see, it gets held low by the device, and that's a 0. And then we see another 0 being pulled. So in all 3 of these bits, the controller is only holding the bus low for that little sliver that you see at the 1 bit. Then the peripheral takes over and holds the bus low for the remainder of that bit time. It's all clear as mud. I know there's a lot of numbers flying around, but let's just sort of look at the maximums and minimums for each of these. So the amount of time you need to hold low to write a 0 is between 60 and 120 microseconds. In order to write a 1, it's between 5 and 15 microseconds. Pretty simple. If we are reading low, we have to wait at least 5 to 15 microseconds before sampling the bus. Sorry, that's how long we hold the bus low. We hold the bus low for 5 to 15 microseconds, and then we sample the bus less than 15 microseconds later, basically is what that's saying. So the only other important part of the bus besides reading and writing bits is the reset and presence pulse. When we first connect to a device, or before we do any commands at all, we issue a reset. That is holding the bus low for at least 480 microseconds. Now that's a pretty long time compared to what we've been talking about. This will actually drain the capacitor inside the device if it's running on parasitic power mode, and it'll do a full power on reset. If the device is being powered externally, it'll act as if it's done a power on reset. It'll see this low period. So as you can see here, the controller pulls the bus low. We are holding it for almost exactly 480 microseconds here. We let go. Then a brief time later, typically about 40 or so microseconds later, if there's any devices attached to the bus, any one-wire devices at all, they will pull the bus low. for about 100 microseconds there, and that's called the presence pulse. If you can see that, that means that there's a device there. It got the reset command and it's resetting itself, and it's basically saying, here I am, I'm on the bus. I pull the bus low for 480 microseconds. They will briefly pull the bus low after the reset pulse, and that's called the presence pulse. As you can see, it's actually decoded for us in the logic analyzer software. It says presence true. So let's look at sort of an example bus transaction putting all this together. At the start there, we have the reset, followed by the presence pulse. Then we send a command. We're going to go over the list of commands in a bit. We send a command, and then we start issuing read slots, and we read the response back. And that's it. There's no clock. It's just a series of pulses, and you have to be able to decode them based on your knowledge of what is going on both sides. So every transaction has to start with the controller sending one of these following commands to determine which device on the bus it wants to talk to. Read ROM, match ROM, search ROM, skip ROM, you see a theme, resume, overdrive skip ROM, overdrive match ROM, and we're just going to look at the most important ones. We're not really going to be looking at overdrive much this week. It's basically the exact same thing, just at a higher speed. So let's go through these. These have codes that are in the standard. So these codes mean these things when they're sent, and that's like all the devices are programmed to recognize these codes. Read ROM, 33 in hexadecimal. This basically says, I want to read your 64-bit serial number. And if there's a device on the bus, it'll respond with its 64-bit serial number. That's a problem if we've got more than one device on the bus. We might have more than one device responding. In this case, every 64-bit address that's sent has a CRC checksum. And if you're actually checking this, it'll be obvious if more than one device responded, because that CRC checksum will not be correct. If that happens, if there's more than one device on the bus that you don't know the addresses of already, then you can issue this search ROM command, which we'll get into later, and you go through this very complicated process to figure out the addresses of every single device on the bus. But if there's just one device on the bus, it'll return its 64-bit address. Pretty simple. Match ROM. This is hexadecimal 55. This is used to address a device on the bus for further communication. So we send 55 followed by the 64-bit address of the device we want to communicate with. We are telling it we want to match this ROM to a particular device, this ROM serial number. Then it communicates with that device, and all other devices will remain idle. Skip ROM. This is hexadecimal CC. This completely ignores the addressing process. This can only be used if you are certain there is only a single device on the bus. Because if you issue the skip ROM command, anything that's listening is going to respond, because it's not checking the address of that device. It's just going to respond. This is the simplest way to implement things when there's only one device on the bus. And if you know there's only one device on the bus, this makes things a lot easier. Instead of having to read the device's ROM address and then use a match ROM, we can just skip this addressing and then communicate with it. So be sure there's only one device, or that you actually want to send the same thing to all devices. There might be cases where you actually want to do that. A resume command. This is hexadecimal A5. After a successful match ROM command, the device that was addressed will sort of remember, I was the last one that the controller talked to. And if I see a resume command, that means it wants to talk to me again, but it doesn't want to go through the whole match ROM process again. So instead of having to send the address, it just sends this command, A5, and then it can do another transaction with that same chip. It wants to communicate with the same device it previously addressed. This is almost like a repeated start from I2C. We're basically saying we want to talk to you again right away. Not quite the same thing as a repeated start, but it's sort of the same concept. Often as in I2C, used to read back the response to an earlier command. You know, do a temperature measurement. Okay, resume, read back the results of that temperature measurement. Search ROM, F0 hexadecimal. We save the best for last. Because when this bus was designed, it was designed to be robust and reliable. You needed a way to determine what devices were on the bus without, in I2C, if you wanted to see if there's devices on the bus, you can just try reading from all 255 addresses. That's not that many addresses. You'll get through them pretty quickly. We've got a problem with one wire. We've got, 10 to the 19 addresses. We can't possibly do that. So in order to simplify this, we can do something called a search ROM. This uses a binary tree, it's hexadecimal F0. It starts an enumeration process. So every single device on the bus will send its address to the controller, but in this special pattern called a binary tree. You start at the top, and then you pick one direction to go. You can go to the right for a 1 or a left for a 0. The right and left, the actual tree is just for humans to sort of understand what's going on. All the devices will start talking at once. How can we possibly figure out which device is which? Say we've got 10 devices on the bus and we're trying to get the addresses from all of them. They're all going to start talking at the same time. So we send the command F0. After that, we will issue 2 read slots. We're going to read 2 bits back. If the device responding has a 1 in the first bit of its serial number, it will send a 1 in the first read slot, and then it will send the opposite of that first bit. So if you have a 1 in that position, you send a 1. If you have a 0 in that position, you send a 0. Then on the second read slot, whatever you sent on the first read slot, you send the inverse of. So this will make sense in a second here. Then we pick, depending on what devices responded, if only devices with a 1 in that position responded, we want to go down that direction in the search tree, so we're going to respond with a 1. And then we move on to the next bit of the serial address, and then we repeat this process over and over again. Therefore, there's only 4 sequences that can happen during this bit search. The first bit is a 0 and the second bit is a 0. Well, that means that there's devices that have both 0s and 1s in this bit, because devices sent both a 1 and the inverse of a 1, which is 0, and a 0, which is the inverse of a 1, the inverse of which is a 1. So in both read slots, we had a 0. So that means we can go in either direction on the binary search tree. If we got a 0 followed by a 1, there's at least one device on the bus that has a 0 in this location of the serial address. If we got a 1 and a 0, there's at least one device with a 1. And if we got 2 1s, that means no devices responded at all. This either means we're finished with this whole process or there's no devices on the bus. The controller will choose which path it wants to continue down. So let's look at an example. And then once we select which direction we're going, if we didn't pick the direction that a certain device has, say we're picking a 1 from that point and it has a 0, it'll just shut up until we get all the way back around to the beginning again. Let's look at a very simplified example of this, because I know it's very confusing. We repeat this 63 more times for a 64-bit serial number. Whenever we have the 0-0 condition, where there's devices that have both 0s and 1s at this bit position, the controller, according to the standard, should always pick the 0 path first, then the 1 path the next time around. So we follow this binary tree pattern, repeat it until every device has been enumerated. So this is sort of what that looks like. This is just the very top of the tree. We send 0 by F0, and then we read back either 1 0, 0 1, or 0 0. Let's say we want to pick the 0 direction. We send a 0 out on the bus, and then any device that has a 0 in the very first bit of its serial number when we send out 2 more read slots, it'll send out the second bit of its serial number. Any devices that had a 1 in the first bit, they're just going to have to wait until we come all the way back to the top of the tree, and then we start over with a 1 in the first bit position. Here's a very simple example. We have 2 devices on the bus. For this example, we're just going to look at 4 bits. Device 1 has the serial number 0110. Device 2 has the serial number 0011. In the first bit position, both devices have 0. So the 01 pattern is sent. So the controller will issue 2 read slots. The first read slot, it'll get a 0. The second read slot, it gets the opposite of that, which is a 1. Because we get that particular pattern, we know that there's only devices with a 0 in this bit position. And if we look, there are. The first bit is 0 for all the devices on the bus. So we write a 0 back because we want to continue with the devices that have a 0 in that position. Because there's no devices with a 1 in that position, so writing a 1 would be pointless. We write a 0. The second position, device 1 has a 1 and device 2 has a 0. As you can see, we have our first conflict. So we're going to get the 00 pattern sent back. There's both a 0 and a 1 at this bit position. According to the standard, we're supposed to go with the 0 direction. So we'll write back a 0, we'll select device 2. Device 1 is going to go silent from this point because we've chosen a branch that deviates away from its serial number. At this point, the rest of device 2's serial number is going to be read out because it's the only remaining device. So we finish reading out its serial number. Then we go back to the top. We issue the search ROM command again, start from the top of the tree, but wherever we forked last time, this time we're going to take the other branch. So this time around, device 2 knows that it has sent its entire serial number already, so it's going to remain silent. It's enumerated. We've got its full serial number stored in RAM. It's just going to shut up and let us deal with the rest of the devices on the bus. Because there's only one more device, now we're going to read out device 1's entire serial number. Then, after we read out device 1, we're going to send the search ROM command again, because we don't know if there's another device possibly. No devices are going to respond. We're going to get the 1-1 pattern, and the search ROM process is complete. Oh my god. So complicated. This is actually supposed to say how to avoid search ROM. Whoops. You don't want to implement this if you can help it. It's complex, it's sort of hard to wrap your head around, and it's honestly, there's very few use cases where you would actually need to do this. Unless you're doing mass production of devices, and the first time they power on, they might need to go through this process to figure out their own serial number or whatever the case may be. But if you're just a hacker designing a simple device, you can just read the serial numbers using read ROM. Just, make sure you've only got one device on the bus. Because it only takes a single GPIO pin, you can just put each device on its own GPIO pin. So there's lots of ways to avoid match ROM. So let's look at these ways, to avoid search ROM. That's the typo on the title there. So this algorithm is painful to implement, so let's avoid it if at all possible, right? If there's only a single device on the bus, we can just use skip ROM. We can just skip the matching process entirely, and that's a good way to avoid it if you can. If there's multiple devices on the bus, we'll connect them one at a time if we can, read the ROM of each, and store them in a constant variable, and then from then on use match ROM. You can do this in a one-off device. If you're just making a one of something, you can physically connect one device, read its ROM, store it, disconnect it, connect the next device, read its ROM, etc. And that way you'll avoid having to do search ROM. It's much easier to do one of these options than write the search ROM code. Maxim have provided an extremely detailed application note on the search ROM algorithm, of course, because it's so complicated. It includes example C code. If you really do need to use search ROM, you can use their example C code. There's a link to that application note. It's good to know about. It's good to understand sort of generally how it works. But in most cases, you want to avoid using search ROM if you can. All right. So now we've covered all the different protocol-related things. Let's look at the software level. All right, so everything is done typically through GPIO. Very few microcontrollers have a hardware peripheral block, as we mentioned before. Therefore, everything needs to be implemented with GPIO pins, just plain old input-output pins. Take advantage of open drain output if the chip supports it. Many PIC devices do. For accurate timing, we can either use a timer module, or we can simply issue NOPs, no operations, for a certain number of processor cycles and just do a software delay. We're just going to use a software delay in our simple example because it's a lot easier to implement, and you can sort of roughly calibrate it through trial and error if you have a logic analyzer to look at the bus. So we're going to take a look at the GPIO section of the data sheet or family reference manual for the particular chip that we're working with. The quirks of each chip can make it easier or more difficult to implement, and it's good to know what you're dealing with before you dive in. We're going to need to switch the pin between being an input and an output quite often. Some chips can do this in a single instruction, which is really good. That'll speed things up for us. Open drain can also make one wire easier. Unfortunately, the MSP430 doesn't support open drain GPIO pins, but that's okay. We can work around that. Basically, we're going to set the pin as a low output, and that'll bring the bus to a ground when we want to bring the bus low. Then we're going to set the pin as an input and at least set high. That's going to tri-state the pin, which means it's going to let go of the bus. It's basically going to be high impedance and not do anything to the bus at all. So just by switching between these two states, we can bring the bus low and then release it to go high again. Remember that we don't actually want to set the bus to an output high, because then we're going to be driving the bus, and the devices we're talking to are going to have to try and pull the bus low, even though we're sourcing, potentially up to 20 or 30 milliamps, which is just not going to work. So let's take a very quick look at the GPIO section of the family reference manual for the MSP430. All right, so here's the family reference manual for the TI MSP430 that we're using. Section 12 is the digital I/O module. Basically, we're just going to take a quick look at what registers are available and the operation. So every port has input registers to set a bit low or high, or to read the state of the bus. It has output registers, which will set the corresponding I/O pin. If the pin is configured as an input direction and the pull-up or pull-down resistor are enabled, then we can turn that pull-up resistor on or off by writing to the output register while it's in input state. We're not going to be doing this because we're using an external pull-up resistor. So we're going to make sure that the pull-up resistor is not enabled. By default, that PXREN is going to be disabled for our pins. We need to switch the direction back and forth, so we'll need that register. Output drive strength register. This could be a way to give the peripheral device that high current peak if it needs it. Instead of connecting an external transistor across VCC and the one-wire bus, you might just be able to set the bus to an output with this full drive strength. That will, as it said, will increase EMI, but it doesn't really matter in this case. That'll probably source at least 20 milliamps, if not more. Again, I/O function is selected for this pin. We don't want the peripheral module function because we're going to be doing everything as a GPIO. We're not worried about interrupts. So basically, we're just going to be using these registers. Actually, we're only going to be using the PX in, PX out, and PX dir. That's it. Everything else is just going to be left as default. So pretty simple, actually. Okay, so let's take a quick look at timing as well. So to do these software delays, there's a header file for the MSP430 called intrinsics.h. And it's got a function called delay cycles. That's 2 underscores delay single underscore cycles, which simply executes no operations for however many cycles we tell it to. We're going to test out different delay times through trial and error. Once we sort of figure out the number of cycles that corresponds to the amount of delay time we want, we're going to store those numbers and then we'll use them when we're writing our code. That's actually, those numbers that just appeared there are the numbers that I figured out using my chip running at 20 megahertz through trial and error. For example, to get a 480 microsecond reset pulse, we need to delay for 9,800 clock cycles. You can sort of calculate this based on the clock speed of the chip, but there's other factors that play into it. Doing it through trial and error is usually the best way to do it. And a good way to determine if your timings are correct is to use a logic analyzer, because you can just send one-wire bits out without actually knowing if there's a device there or not, and just have the logic analyzer look at them. And if it's able to decode what you're sending, it will, that's a confirmation that your timings are good. A nice thing about Pulse View in particular, if your timings aren't good, it will usually tell you exactly what's wrong. The read slot is too short, the read slot is too long, the reset pulse is too short, no presence pulse detected. It's really good at actually giving you feedback on what's wrong, which can be really, really handy. So again, these numbers here are only applicable when running at 20 megahertz. If you're using the example code from our GitLab repository, then it will be running at 20 megahertz because that's how the chip is configured. So the reset pulse, we're going to write a separate function for it as it gets called before every single transaction. It's got to be 480 microseconds long. So we set the output low, we wait for about 500 microseconds, and then we set the GPIO pin to an input and high, which tri-states it and disconnects it from the bus. This is what that actual snippet of code looks like. We're using port 2, pin 2, so all the registers are going to be P2 and then out in direction, and they're all going to be working with bit 2, which is pin number 2 of port 2. So first thing we do is we set the output low. We wait however long it takes for the reset pulse, 480 microseconds. We set the pin high, and at the same time we set it to an input, so it disconnects it from the bus. So the presence pulse, after the reset pulse is complete, we then need to wait and see if we get a presence pulse from any devices on the bus. If we get a presence pulse, this function is going to return a 0. If we don't get a presence pulse, we're going to return a 1. This allows the program to decide how to proceed if there is no response. We're going to delay, so this is leading off from the code we just saw. We're going to wait about 40 to 60 microseconds. We're going to check to see if there is a presence pulse there. Basically, we're looking at bit 2 of the input. If it's a 0, that means we have a presence pulse. We're going to do a bit of housekeeping, which is we're going to set the bit to an output again, still set high. We're going to wait and finish out the reset, and we'll return a 0. Otherwise, we'll do the same thing. We'll set bit 2 to an output. We'll finish out waiting for the appropriate amount of time, because after the presence pulse, the devices need a little bit more time until they're ready. We'll return a 1, although in this case we didn't get a presence pulse, but we're still going to delay. And that's it. So the actual transaction function, similar to I2C like last week, I write a single function typically that takes a pointer to the data that is either to be transmitted, or it's a pointer to the buffer where we're going to store data that we're reading, the length of data to be read or written, and a variable to indicate what type of transaction we want, whether this is a read or a write. This function is actually a lot simpler than the I2C transact function because one-wire is a much simpler protocol. If we're reading, we just bring the bus low for 5 microseconds, and then we read the state of the bus to determine what bit we're reading. If we're writing, we simply hold the bus low for a different length of time, depending on if it's a 0 or a 1. It's that simple. Unlike the I2C library, commands, addresses, and data are all sent the same way, and they're all treated as data. So there's no separate registers for the address. Everything is treated as if it's data. So the one-wire library itself doesn't actually know if it's sending a command or if it's sending data or what. That's up to the end user to implement. So it's quite simple. So let's actually take a quick look at that library before we finish things up here. Okay, so this is the one-wire library. This is the constructor function. I actually made a mistake earlier. I actually am using the internal pull-ups. Basically, in parallel with the external pull-up, it's not going to make much difference. And I guess it was just an easier way to tri-state the bus or to not have any effect on the bus. This sets up one-wire data as being on port 2.2, says the direction as an output, and then it sets it high. So as soon as we enable the one-wire bus, it's going to set the bus to high, which will hopefully charge the whatever device we're using. So this is fully connecting the output driver to the bus to charge up the external device and make sure it's fully powered. We've got our simple function that resets the bus. It assumes that we're actually set as an output, which is, maybe I should probably fix that, but we set the bus low, wait, we went through this function in the slides, and then based on the status of that bus, if it's low, when we have a presence pulse, we return a 0, otherwise we return a 1. And then here's the big transact function. We've got read and a write. And look, this is basically the entire library. That many lines of code. So there's not a whole lot here. Basically, if we're reading, we go through however many bytes we're reading. That's one for loop. Then the internal for loop is going through bit by bit reading 8 bits. So we set the bus low for however long that read window is. Then we set it to high and set it as an input. Then we wait however long to sample the bus. Then we sample the bus. And basically whatever the bus is goes into the byte buffer. And then we set it as an output, which won't actually do anything at the moment. And we wait until the next bit period. And we do that over and over and over again until we've read however many bits and bytes we need to read from the device. If we're writing, very similar thing. We pull the bus low. If it's a 1 in this location, we'll hold it low for a different amount of time and then leave it high for a different amount of time. As opposed to if it's a 0, we just have different lengths of time for holding the bus low and then bringing it high again. That's it. At the end of each bit, we make sure that we've taken up that full 120-second window. Pretty simple. Basically, these 3 variables, 1 low length, 1 high length, and bit period length, or 0 low length, 0 high length, and bit period length, those should all add up to 120 microseconds. That's it. I have a write read function, which I didn't actually implement. Then I have a test, which just sends out a 1 followed by a 0. That's it. And then we have a function here to compare a read ROM, which we're actually going to use for our really simple example here with the DS2401. We take a variable that's stored, which is 8 bytes long, 64 bits, and then we take a variable that we've received from the device. We compare them together. If they're the same, we return the fact that they're the same, and if there is a difference between them, then we return 0, basically. And that's used in our main function to determine if we're talking to the right chip. It's a very simple example we'll see in a minute. The header file just has all those different delay times defined, as well as the command types we might want to send, just as sort of a convenience for the end user. And the declaration of a class, and that's it. So let's quickly switch back to the slides here. We have a very simple example. I wanted to write a very simple example just to see if the code was working. I had a DS2401 in my stockpile. This is the simplest one-wire device that exists. It's called a silicon serial number. All it does is respond to read ROM commands and reply with its 64-bit unique address. That's all it does. These are chips that are often used to give a board a particular serial number so that it can be identified for quality assurance or whatever. It can also be used for any other need. If you need a 64-bit number for something, maybe as a random number seed, or for any purpose you want if you need a 64-bit unique number. The data sheet for this particular device is there, but it's literally so simple we're not even going to look at the device. We're just going to issue the read ROM command, compare what gets back to with what I know the correct value is. If it's correct, we proceed. If it's incorrect, we basically stop the chip because there's something wrong. And otherwise, we'll proceed into the code from last week where we read the temperature and humidity from the SHT chip. So this is basically just adding in a one-wire device as a fail-safe to make sure we have a valid device. This is sort of a contrived example. So let's take a very quick look at that code. So let's switch back over to Code Composer Studio. So here in the main, now we're also creating a one-wire device, OWB. Up here I have the stored serial number. This is what I know my chip has. So I stored that as a const. Then down here, the first thing we do is we reset the bus. We send the skip ROM command, which is just a write of 1 byte. We read 8 bytes from the bus, which is going to be the serial number of this device. Then we use that function I showed to compare the stored serial number versus what we just read. If they're not the same, we're going to print this to the output. Critical error, ROM number mismatch. All your base are belong to us. And then we'll return from the main function, which basically, it doesn't actually crash the processor, it just halts. And then you have to do a power cycle. Otherwise, we'll go into our code from last week where we start reading the humidity and temperature. So this is something you might actually do in a real world scenario. You want to check that this device is valid for whatever reason. You want to make sure it's your device or that it hasn't been tampered with. This is one way to do it. You check the serial number of a one-wire device. So pretty simple. If we actually go back to the slides, that's what that example transaction we were looking at earlier was. This is us sending a reset pulse. Then we get the presence. We send the read ROM command there. You can see it's hexadecimal 33. Then we get this huge 64-bit value back. It's actually flipped around from the way I have it stored because of the way this decodes it. Pulse view actually assumes that it's least significant byte first. Which is normally how it would be displayed, but I have it the other way around in my code. It doesn't really matter. And that's that. Pretty simple example, but it shows that our code works. And it's, a very contrived example, but one that you might actually see in the real world. So, a quick summary of everything we went over. One-wire is slower than I2C, but it's a simpler protocol to implement than many other serial protocols. It's great for acting as a unique serial number for your circuit if you need a unique serial number. It's usually implemented as bit banging with GPIO commands the way we've done it. With some exceptions, there are some chips that have built-in one-wire peripheral blocks. Not a lot of chips do because it's so simple to implement. The hardware level is similar to I2C. External pull-up resistors are required. It's often very fast to prototype and test, especially if you have a logic analyzer to confirm the timing of everything like I do. Writing that code was very quick because I already knew the one-wire protocol, but also because with an external device like a logic analyzer to confirm your timings, you can very rapidly make changes and get everything dialed in. It's excellent for low-power devices running on batteries. One-wire devices, when they're not in use and they're just sitting there, take very, very little power. Many of them you can just turn them off completely. You can just bring the one-wire data line low, and if it's running on parasitic power, you can literally just shut the chip off, which is a good way to save power. So additional resources. Oh, another slide that's all glitched. Maxim have an entire section on their website, which is a guide to one-wire communication. There's the link. Almost all one-wire devices have a great summary of the essential pieces of the protocol, just like I2C. They'll have an overview of the basics of the protocol. If you have any questions, feel free to comment on the project page on HackadayIO for this course. That way everyone else can see your questions and they can see my answers there. Or tune into the Q&A Thursday evening, 6 p.m. Eastern, the day after this course goes live, this particular class, and feel free to ask any questions there. That's it for OneWire. Next week, we're going to be combining everything together and reading from both I2C and OneWire chips and combining it all together into an actual project. So thank you so much for tuning in. Hopefully we'll see you tomorrow night if you're watching this as it's come out. Hopefully we'll see you at the Q&A. If you have any questions, go to the HackadayIO page. And thank you very much for joining us for the week 3 of this course.